discussing about liquid-vapor equilibrium and the equilibrium law. Okay, in liquid-vapor equilibrium, it's actually an example of a physical system in equilibrium. In the previous part, we discussed mainly about chemical equilibrium, but this is a physical dynamic equilibrium. Okay, so in this, you will need to discuss about evaporation and condensation of liquid, evaporation of the liquid and condensation of the vapor in a closed system. Okay, so at equilibrium, the rate of evaporation will be equal to the rate of condensation. Okay, and the pressure exerted by the gaseous molecule at this point of equilibrium is what we call the vapor pressure. Okay, we can treat this vapor pressure almost like the equilibrium constant in the chemical equilibrium. Almost like that, it's actually not. But this vapor pressure is constant at the same temperature. So similar to equilibrium constant, the value of vapor pressure is only dependent on temperature. For example, you can reduce the liquid inside here, but at equilibrium, it will still have the same vapor pressure. You can make the container bigger or wider, but at equilibrium, it will still give the same vapor pressure. Okay, so you need to emphasize this to your students. Okay, and also how vapor pressure increases with temperature. Okay, because as you increase temperature, the rate of evaporation will increase at the beginning. Okay, but that's already enough to increase the vapor pressure. Okay, be careful when you're explaining this. Okay, when you increase temperature, the rate of evaporation only increases at the beginning. If you leave it, the system will again reach another equilibrium. Okay, so at that time, again, the rate of evaporation will be equal to the rate of condensation, but probably at a different level than previously. But at that time, already the vapor pressure increases. Okay, so you need to know that as temperature increases, vapor pressure will increase, and your students need to be able to explain that as temperature increases, vapor pressure also increases. Okay, now if you realize the vapor pressure is exerted by the gaseous molecules, right? Which means the more gaseous molecules you have in the system, you will have a higher vapor pressure. You need to explain to your students the link between this vapor pressure and intermolecular forces. Okay, we know that the weaker the intermolecular forces, the easier for the molecules to break this force. Okay, so when your intermolecular force is weaker, okay, there will be more gaseous molecule in the system, just because when the intermolecular forces is low, it's easier to evaporate. Okay, so the greater the vapor pressure, the lower the intermolecular forces. Okay, so for example, if I have two graphs like this, okay, one is substance A and one is substance B, at the same temperature, okay, the one with a higher vapor pressure will have a lower intermolecular forces, which means A has a weaker intermolecular forces as compared to B. Okay, this will also lead to lower boiling point and lower enthalpy change of evaporation. Okay? So these are the relationship between vapor pressure to intermolecular forces, boiling point, and enthalpy change of evaporation. Okay? When you mention about boiling, you also need to tell your students that boiling happens when vapor pressure is equal to the atmospheric pressure. Okay? So for example, if this is 1 atm, which is our normal pressure, to find the boiling point of A and B, you just have to draw a horizontal line. So this is the boiling point of A, and this is the boiling point of B. Okay? Now, for the equilibrium law, okay, the equilibrium law involves the calculation of different concentrations of product in the equilibrium, or they can also ask you very simply what is the Kc of the reaction depending on the concentrations at equilibrium. Okay, so yeah, this part can be explained more clearly with the aid of a sample question. But what you need to be teaching your student is this method called the ice table. Okay. So for example, if I have an equation, like in this case, the formation of ammonia. Okay. So I'll list this here. Okay, because all these three species will be in the equilibrium mixture. Okay. So you need to determine the initial concentration. You need to determine the change so that you can arrive at the equilibrium concentration, which will be used for Kc. Okay, so for example, if they say they start with 1 mole per dm cube of hydrogen, okay, and 2 mole per dm cube of nitrogen, and they will say something like maybe 10% is converted to ammonia. Okay, so we know that initial concentration is 1 and 2 and 0, and I know 10% is converted to ammonia, which means 10% of 10% of hydrogen is converted to ammonia. Okay, so you know that 10% of this is 0.1, so the change is 0.1. Okay, and based on the stoichiometric coefficient, 2 is to 1 is to 3, 0.15 of this must have reacted and 0.05 of this must have reacted, and you will have 0.85. Okay, then you calculate the Kc. You know that the Kc expression will be product concentration to the power of stoichiometric coefficient and reactant concentration to the power of stoichiometric coefficient. Then you just have to sub the numbers in. Okay, there will be variation to the question, then you just have to adapt this method accordingly. Okay, very importantly, again, mention to your students, right, in Kc, this concentration cannot be any concentration. It must be the concentration of the products and the reactants at equilibrium.